So, hello everybody. Um, my name is Jerry, and so I think today we're going to be doing AP Physics 1. I think this would be very useful for anybody in this meeting who wishes to take AP Physics 1 in high school. So we're just going to go over what the AP exam is kind of like, and we're going to do some practice problems that can help you get a feel of what kind of problems are needed or are asked. Do you need to know calculus? No. For Physics 1, you do not need to know calculus. It is Physics C where you have to know calculus to be able to attempt the test. Yes, you have to know what trig is, because Physics 1 does ask about simple harmonic motion, which if you have watched some of our other lectures detailing that, you know that revolves heavily around knowledge of how the trig functions work. So yes, you do need a trig, and you do need some degree of pre-calculus in order to do Physics 1, but you do not need calculus, and you do not need other advanced math topics. Okay. So yeah, basically, obviously there's the AP Physics 1 class that you would take in school to help help study for this exam, but the exam itself is 3 hours long. This is in contrast to Physics C, which is half of that time period. Section 1 is basically your multiple choice section that you would see in other tests, and you would have 50 multiple choice questions, and you have 90 minutes to solve them. Section 2 has 5 free response questions, and you're also given 90 minutes. Note that these free response questions, though, do always have multiple parts. So even though it says 5, that's just 5 questions in total, and there's always at least, usually at least 4 parts in the question. Both of these sections each account for 50% of your score in the AP exam. If you're curious about how AP Physics C works, Section 1 in Physics C is 35 multiple choice questions for 45 minutes. Section 2, if I remember correctly, is 3 free response questions, 1 calculus. One is always a calculus question, 1 is usually a rotational motion question, and 1 is a lab experiment question. You're given 45 minutes for each section, and like Physics 1, each one would also count as 50% per score. Physics 1 has 7 major topics. So kinematics, which is basically general motion, it's predicting paths most of the time of some object in motion. Dynamics basically means forces. So this is force studies. Basic circular motion. We do not do rotational dynamics in Physics 1 that much. You might get some questions asked about what moment of inertia is and what is the moment of inertia of some things, but you do not have to go deeper into it, and they will not ask you to prove that the moment of inertia is something. Gravitation is basically gravity between celestial bodies most of the time. Energy, momentum, simple harmonic motion, torque, and rotational motion, which is basically usually covered in the same unit as circular motion, although this might differ. So I guess we'll just get started on the problem. So basically, these types of problems are ones that are from Physics 1 practice books, and they kind of help give you a feel about how Physics 1 is going to work. Most classes would give practice tests or make their exams in the class, similar in style to the AP exam. So these kinds of questions would be a very big help to learning and mastering time management and also the concepts. So question 1 is a kinematics topic, and it's basically detailing a thrown ball. Now, since this ball, as you can see in this diagram, is thrown at an angle, this means that the path would be parabolic. Assume friction is negligible, which you can assume for every single problem in Physics 1. If something is being dropped, you can always assume that friction is negligible. Point Q is the highest point on the path here, and points P and R are the same height above the ground. How do the speeds of the ball at the 3 points compare? So basically we know at point Q the speed is 0. This is because it is at its maximum point. So you can imagine the speed versus time graph as initially positive and going down at a constant rate, so a decreasing linear function until it hits 0 at Q. Now, when V, here we mean velocity, when V hits 0, that means that the speed is also 0, and that means that the point has reached the zenith, or like highest point, because after that, V will fall, and then that means that the object is starting to descend. So we know at Q the speed is 0, and P and R are the same speed. Now, why are P and R the same speed? You can just derive this using your basic kinematic equation in respect to position. So yeah, the only difference is that if you're not talking about speed and instead talking about velocity, R would be the negative in terms of P. But in terms of the magnitude of the velocity or speed, as we're trying to find here, they are the same because they're the same height above the ground. It's always like this if it's symmetric and it's just general motion. So the answer here would be D. Are there any questions? If so, if you guys have any questions, just unmute your mic and say it, because I can't see the chat box while presenting. So it will be easier to just unmute yourself and ask if you have any questions instead of putting it in the chat box. So yeah, that's basically what we kind of went over. The vertical component of the velocity is 0 at the top, and that means that the minimum speed is at the top of its trajectory. Now, and then due to symmetry, any projectile would have the same velocity, same speed, sorry, if they're at the same height. Now, question 2 uses the same diagram as question 1, which is an object being thrown in a parabolic motion. And it's asking which of the following diagrams best shows the direction of the acceleration of the ball at point P. Now, this is this kind of question, this is a completely conceptual question. These two questions are completely conceptual, and you do not need to do any calculations. It's very important that you understand the concepts that go into these types of questions, because that's what they're basically testing. If you do not know the concepts, you're gonna get it wrong. So what they are testing you here is whether you know how acceleration works in basic two-dimensional motion or general motion. So acceleration is always A, and A being G. So basically, if you're just throwing something and there's no external forces or anything else involved, your acceleration should always be G. Now, g is the gravitational acceleration of Earth, and that is defined as 9.8 meters per second squared. And then with respect to the object, it's always facing down because the object is accelerating towards the ground. The reason it makes this motion is because there's also motion carrying it horizontally from when you're initially throwing it. So that's why it would look like this. So that your v vector would look like that, and this vertical component will slowly decrease until it hits q, which is just a horizontal component, and then by points like r, the v is going down. So you could see that really the thing that shifts is the vertical part, the vertical velocity, and it shifts down, and it basically it decreases, which means that the acceleration is facing downwards. So the answer is D. Now, question 3 is kind of like what a free response problem, a short free response problem would look like, where it does not ask you to explain answers, and it's basically what you do here is that you show your work in typically a box given, and yeah, so basically you show your work and you box or circle your final answer. It's best if you're doing this is that the best thing to do is always express your answer as a decimal. Most physics teachers and physics exam graders do not really accept like mathematical expressions in your final answer, like the square root of 2 or like pi or something. Okay, so here we have a ball that has a mass of m and is released from rest at a distance h above a frictionless plane, inclined at an angle of 45 degrees with respect to the horizontal as shown above. The ball bounces horizontally off the plane at point P1 with the same speed in which it struck the plane and strikes the plane again at point P2. In terms of g and h, determine each as the following quantities: the speed of the ball just after it first bounces off the plane at P1, the time the ball's in flight between P1 and P2, the distance L, and the speed of the ball before it hits P2. So it's obviously harder. This is it uses here several concepts are used. So for part A, for what's the speed after falling from height h, like before it bounces, you're supposed to use conservation of energy to solve this kind of problem. So what we would see here is that before this is dropped, this is the ball is complete. All the energy in the ball is potential energy. By the time it hits P1, all of that energy is converted into kinetic energy. So here you would use conservation of energy since there's no extra work or force that's being applied to the ball. So that would be mgh is equal to 1/2 of mvf squared. And then you could cancel the m's, move the 1/2 over, and you get vf squared is 2gh, and then just solve for vf. So you get vf is the square root of 2gh. And in this kind of situation, yes, that square root of 2 is allowed because you're simply writing an expression. Okay, for parts B and C, this relies on kinematics. So from P1 to P2, this ball obviously maintains this horizontal speed of 2gh, and it also travels a distance horizontally of L over the square root of 2. This is because the slope is 45 degrees and the slope length is L. So you could say this is L times the sine of 45. Sine of 45 or cosine of 45, they're the same number anyways. Cosine of 45 is 1 over root 2, so you would get a horizontal distance of L root 2. Now, here, since the horizontal speed is constant, you can use the equation d equals vt. So you would just plug it in. So the distance, L square root of 2, is the square root of 2 GHT. And yeah, and you just solve for t. So although they didn't do it here, you could just move this square root of 2 over and then divide by GH. So t should equal to L over 2GH. Now, during the same time t, the ball travels the same distance vertically. So here you're only analyzing the vertical component of this. So the initial velocity in terms of like verticalness is 0. So so you would use your kinematic equation with respect to distance and acceleration. So d would equal to VIT plus 1/2 of AT squared. It's taking a bit long to write, but yeah, I apologize. Now, we know this ball is moving downwards, so A is G and VI is 0. So this term can be completely neglected, and D is just 1/2 of AT squared. So L over root 2 is 1/2 of GT squared. Now, you can solve for T here. So you could get square root of 2 GHT is 1/2 of GT squared. And then you can solve for T here, and then you can substitute that into the expression of L. And then this would be, you get L is the square root of H over G. So L, in terms of that, is just 4 square root 2 H. So does everyone understand that? Okay. So part D, you're still using the fact that the ball maintains a horizontal speed of square root 2 GH. And here you're analyzing for the vertical component of the velocity, since the horizontal part is known. So you'll use this equation, VF equals VI plus AT, and you can substitute in the values that we already know. So VI is 0, remember, A is G, and we've already solved for T in the previous parts. In every FRQ, you are allowed to use the answers you have gotten for the previous part from the previous parts, and then use that same value you obtained into the next part. Typically, FRQs even require that you use information from previous parts to determine the answer to the current part. So here it would be T. So that would give you Vy, and we already know what Vx is. That's just square root 2 GH. So you just use. You guys can do it you guys can try it on paper, but I'll just go over it very quickly since we have many more problems. So the speed is the magnitude of the two of like the general direction. So you have a Vx like horizontal one, and you have a vertical one. So in order to find this the magnitude, you'd use the equation square root of Vx squared plus Vy squared to get this vector. Now, if you plug in the if you plug in what we have gotten from previous parts, you should get V equals to the square root of 10 GH. Okay. Now, question 3 is a force analysis question. So you're given the 3 masses, as you can see this here. This is a pulley system, which is very commonly seen in the force analysis unit. If the coefficient of kinetic friction, or the friction that exists when 2 objects are sliding against one another, if the coefficient of kinetic friction between the large mass and the table is mu, what would be the upwards deceleration of the small mass? The mass and friction of the cords and pulleys are small enough to produce a negligible effect. So basically what they're saying is that like you can ignore any types of gravitational force that's involved with the wire and the pulleys moving. So why won't this? So a very, very important equation that you've probably heard of before, but you'll need this a lot, is F equals ma. So this is Newton's second law, and almost every single force analysis question will eventually involve this equation at some point. Here, if you saw the diagram, the only force that's actually involved once you release the system is the gravitational forces pulling the 2 blocks on the side of the table. So so friction, so this is basically calculating friction. So if you guys remember from the diagram, it was only the second block that actually had friction applied to it. So friction is basically defined by formula as the coefficient times the natural force. Here, the natural force is the same as the weight of the object, which is mg. The reason this is the case is because both of these forces need to balance themselves out for the object to accelerate left or right. If these did not balance themselves out, the object would be accelerating away from or to the table. Yes, N is normal force. Well, this is kind of something my physics teacher said, but yes, normal force should be the same thing as natural force, but most people prefer to just call it a normal force because forces are natural in the first place. Like every force is natural. Like gravity itself, gravitational force is also natural, but we don't call it that. So I'll refer to it as normal force. But if you prefer the word gravitational force, no, sorry, natural force, then yes, what I'm referring to is the same thing. So here, the normal force is equal to the weight. So you just have mu m2g is mu fn. Now, you also should use this. Sigma f or f net is ma. So what this means is that the main thing that's you can like set 1 as like a 0 force, or like one direction as positive and one direction as negative. So here we set the force pulling M1 down as positive. So that means that the force that this like force traveling downwards, I'll use a different color to help you see. This like general direction of motion will be thus considered as positive in this case. So the positive force here is the weight of is basically the weight of M1. And since M3 is also pulling here, and so is M2. So since since m3g and the friction from and the friction from m2, they are both going right and downwards on the right side respectively. These are considered as negative forces. So you would just use m1g minus m2g minus m3g equals to m1 plus m2 plus m3a. So yeah, if you if you solve for a, then you should get answer D as your answer. Torque is more extensively looked into in physics C, but in physics 1, it's still occasionally touched upon. The main difference is that torque in physics 1 almost always is just a force that's just applied parallel with respect to a force that's applied perpendicular to a certain radius. The force is not angled, so the force doesn't go like that, or like some like way that's just not tangent to whatever rotating object you're applying it to. So yes, this is rotational motion. So here you have a system of two wheels. They're fixed to each other, but they are free to rotate independent of one another about one frictionless axis through the common center of the wheels and perpendicular to the page we're looking at here. You can see that 4 forces are drawn. Oh, what is torque? Torque is the rotational equivalent of force. So if you have looked into our, I think like class number 5, which was the lecture on like basic rotational motion, you would know that the setting like the variables and symbols that we use in rotational motion are different with respect to the general motion. So for example, instead of standard velocity, you have angular velocity. So basically what this is that instead of like looking at it linearly, you're looking at it through an angle, because everything you're applying to can be just assumed to be a circle. So for example, omega is the change in angle, is like the change in angle with respect to time, and it can be measured in radians, actually, in radians per second. So here, like in that same kind of like comparison, torque is the rotational equivalent of force. So basically, you can kind of think about it as this: if you have a bolt, for example, that you want to turn, but it's really just stuck there, you would use a wrench, a poorly drawn wrench. And what you would do to this wrench is that from some distance away, you would start pulling this down in a circular fashion. So what you're exerting on this bolt is not force, but torque. So torque is basically force applied in a rotational mode, in like a rotational way around from a certain distance away. So that's actually like the main focus of this question. So how do you find torque? Because they're asking you what is the net torque on the system with respect to this axis. So physics 1 just needs you to know that torque, which is represented with the Greek letter tau, is force times the radius you're applying it away from. Just like velocity is angular velocity, also times the radius that you're applying it away from. But so you can see that kind of like analogous comparison. this is basically what is the main focus here. So here you have four different forces applied. So you have this one here. You have a force that's going this way. A force that's going counterclockwise, and this one has a torque of 2Fr. This one, since the radius of this outer wheel is 3R, this torque would be 3Fr. This F, although it's pointing down, is still applied in a counterclockwise fashion, so we will still consider that to be the same sign as this, even though it's in a different orientation, because orientation is really not a thing in rotational dynamics, and it's mainly just whether you're going counterclockwise or clockwise. So this one would be, just like this one, it would be 3Fr because it's applied on the outer wheel. And then this force here, that's 2F, is applied in the opposite direction. This one is applied clockwise. So we would denote that they're in opposite directions by saying that, let's say, defining this one as positive and this one would then become negative. So this one becomes negative 6Fr because it's negative 2F times 3R. So you just add all these up and you should get 2Fr as your answer. So that's how you can kind of do most torque questions in Physics 1. Now, Physics C demands a little bit more in terms of knowledge of torque, where you would say that the torque vector has to equal to the force vector. It's basically equal to the cross product of the force vector and the radius vector. So basically this accounts for if they're done in different directions, and that basically means is Fr times sine of the angle between them. This kind of like lets you know like the difference between Physics 1 and Physics C. You do not have to know this in Physics 1 because none of the forces that are applied need you to know like an angle in between, but Physics C sometimes does that as part of its questions. So for the most part, Physics C in mechanics is actually just Physics 1, but with like extra topics involved. It's kind of like how BC is mostly AB, but there's some extra topics involved in that as well. Question 6 this is an energy question. You can probably tell it's an energy question because it's something traveling and your main focus is height. That's not really the case with general motion and worse problems. So yeah. So here you have a figure that we're going to assume is a semicircle, and these ends are h meters above the ground. So let's say we place a block here and it starts swinging in between here. So you can think about this. You can visualize this in your head, I guess. Typically, visualizing a conceptual question is very helpful to actually like getting answers, because these do not rely on math and instead rely on your intuition and your knowledge of concepts. So visualizing how this would play out, like imagining that, like, for example, when this is placed here, you like stopped, stop this by, like, for example, just like pressing pause, for example, on space time, and then once you're trying to like simulate this thing moving, you could just imagine how, like, since this is a semicircle, you can imagine how a skater skates in a park. These kinds of like strategy of imagining the problem can be very helpful. And if imagination is not enough, you could just on the side of your paper draw a diagram and just like maybe draw a few arrows that can like help detail the motion of the object. The question is, which of the following is true to the height of which the block rises on the other side of that path? So basically what happens as this reaches here. And we're going to assume down here, this is the height of 0. So the correct answer is actually D. You cannot say for sure what the height will be because we actually don't have enough information about how much energy is conserved throughout the motion of this object. So, for example, if this surface is frictionless and there's no external force applied, then by conservation of energy, this would rise to the exact same height up here. So this would rise to point P and just oscillate through these. However, if this surface of the track has a lot of friction, this would immediately start slowing down on the road down, and it would basically stop at the 0 point and just stay there. So the exact height of this really depends on how much friction there is and how much energy this friction claims, which is basically the work done by the friction. This is another this can be extended to rotational analysis since this is a swing, but here you shouldn't be fooled by this, and it never asks for any kind of like reference to like velocity or anything relating to that. So this is not actually a circular motion problem, but it is actually a force problem. So oftentimes a problem can appear to be like relating to one topic, but you actually may not need to know that topic, may not need to like apply that like knowledge from that topic at all. This is kind of like this kind of deception problems that are just there to waste your time. So here, this looks like a rotational motion problem, but they never ask for anything relating to rotational motion. So this is actually not, this is not a rotational motion problem. This is a force problem. So here you have someone that's like pushing a kid on a swing that's L meters long in terms of the rope length, and it's offset initially by an angle theta. The child has a weight W, so here W is mg, and we're going to forget any kinds of like we're going to forget about any kind of like aerodynamic resistance, like how it has while in motion, or like any kind of like uneven distribution of weight through the child's body, and assume that the child is a single point. We're also going to ignore the seat weight and the weight of the rope. So physics 1 often uses ideal scenarios. So it's very rare that you would find a question where these kinds of like external parameters are taken into consideration, which actually makes your life easier. And yeah, like knowing that most problems would forget about that would kind of like ease up like the complication in terms of math and other types of analysis. Okay, so here the letter L was accidentally just not typed, but here's in terms of W and L, we are to determine the tension in the rope and the horizontal force exerted by the adult. So how you attack any actually, no, it would not. That's because you're only looking at the vertical component of it and you're forgetting that there's a horizontal component. This L is actually at an angle, which means that there's both a vertical and horizontal component. Tension in like any chord should always follow the direction of this like stretched out chord. So like even if it's like at angle like 45 degrees, that means the tension here, the tension from the two ends is always at a 45-degree angle. So yeah, no, it's the direction of the tension should be directed up like this way. Okay, well, anyways, you still actually need to use the weight. That's because like I kind of just said before, there is a vertical. You should like analyze the tension by taking it apart by the components. So there's a vertical component and a horizontal component of tension, and just taking the square root of the sum of their squares should give you the magnitude of the tension. So at any the first step you should always do in any like force problem is to draw a free body diagram, because this allows you to analyze every force and take into consideration and just not forget the important forces at play. So what's the main forces here are, there's two forces. So there's the gravitational force, or the weight, that's being directed downwards, and there's the tension, which is directed in it should be directed here, and then this is 90 minus theta. Should be directed in this direction. So since the child is not after the parent releases the swing, the child should be swinging this way, like horizontally. We know that there is no net vertical force. That means that this W and the vertical component of T must cancel each other out. I'll move on to the next slide to just check to see if I drew the diagram. It's here. So you can see here, there is the force that's being applied by the parent. There's the gravitational force of the child, and there's the tension, which is theta right from vertical. So like I said before, you use F net y equals 0, and we know that T cosine theta minus W is 0. So T is W over cosine theta. Just move W and divide by cosine theta. So so basically most force questions would have at least one component equal to 0, and you're supposed to use that equation to find a component and then apply it to like the overall force. This is basically the way to go for most force problems. Draw a free body diagram, identify any net forces that might have been given the problem. Here it's 0. A lot of the times it's 0, and then solve for anything that you can, and then apply the properties that you now know and attempt to solve for what they're asking for. The physics free response questions often have questions like these where they just ask for a expression. It's best to make these legible and clear and make sure they're boxed. Now, question B asks for what was this force that was applied by the parent. So like we kind of did earlier on, we have to use both of. We kind of have to use both here. When the parent is holding this child, is holding him, is like basically that means the child is in complete equilibrium, and he is not accelerating vertically nor horizontally. So both F net x and F net y are 0. So you have T cosine theta minus W is 0. And then you have T sine theta minus FH is 0. So in part A, we solve for T. Like I said before, you can use previous answers to get like answers that you need. So here, what we mean by that is that since we know what T is, we can just substitute T in. So T is W over cosine theta. So you have W sine theta over cosine theta minus FH equals 0. And thus, uh, this expression is FH. Now you always need to simplify. So here what you can simplify is sine theta over cosine theta. This is tan theta. So FH is W tan theta. So yeah. So does everyone understand how I got that? Okay. Okay, if so, I'll move on. Okay. This is a momentum problem. So this is also kind of like one of the parts where AP1 and APC differ, in which APC goes into this a lot more complicated, a lot more like in a complicated way than AP1. AP1 needs you to know that momentum, you need to know what momentum is, conservation of momentum, and the three different types of collisions. So elastic collision, inelastic collision, and a perfectly inelastic collision. You need to know how they behave, how does energy work in each of these cases, and how do you apply both like energy equations and the conservation of momentum to solve for properties like velocity or acceleration. So another thing you have to know is that impulse is force times time. You want the three collisions again. So you have elastic, where two objects collide into each other and no kinetic energy is lost. So that means that they hit each other and then they bounce off in two directions, and there's no energy that's dissipated in the collision. Partially inelastic is the same thing, except there is some energy dissipated. Now, in an inelastic collision, the objects join together after they collide, because a perfectly inelastic collision maximizes the amount of energy lost, which and in the case of collision, that would be maximized when the objects join together and travel as one entity. So those are the three types of collisions. Here, you also need to know that momentum, which is expressed which has the symbol J, is force times time, and is also equal to the change in momentum. So in most cases, you do not need to know that this is not really a linear equation for most of the times. It's technically the integral, but then again, you don't do calculus in physics 1, only in physics C. You do, however, need to know that because it's an integral, impulse is the area under a force time graph, which is what this question is actually asking about. So here you have a 2 kilogram object that's initially moving with a constant velocity, and it's subjected to a force of magnitude F in the direction of motion. And you can see there's a force time graph applied here as well. Now, here what they're asking for is what is the increase in the velocity of the object during the time the force is applied. So here we always start off with impulse is the change in momentum. Impulse can be calculated by finding the area of this trapezoid. So you can divide this based on these partitions that they kind of already gave here. So these two triangles each have an area of 1, and then this square has an area of 4. So that means that this total impulse is 6. So P, if you guys remember from our lecture earlier on momentum and collisions, is mv. So we would just put this as 6 is equal to, since this object remains as 2 kilograms, we would have Q times VF minus VI. And what this problem is asking for is, what is this VF minus VI value? It's the change. What is this change in velocity? So you just divide it by 2 and you get 3. So here your answer will be 3. So everyone understand? This is one of the harder units that physics 1 gets into, and that is spring oscillations, where you have to know how energy works, and you have to know how trigonometry works. So more specifically, you have to know how a sine cosine graph looks like. So you have to have taken some kind of degree of algebra 2 or pre-calculus before taking this. The sine cosine graph appears as a sinusoid, for those of you guys who know. It basically looks like this. This is a wave. This is like a wave-like function. It's a wave-like function. And most waves in physics, such as like an object undergoing oscillation, can be modeled in such ways where the only thing you're really changing is how like steep the slope of the wave is. Basically, how compressed are they, what's the height, and stuff like that. Here you have a 2 kilogram block and it's attached to an ideal spring, where K is 200 newtons per meter. And it's initially at rest on a horizontal frictionless surface. Now, in this experiment, in this diagram, as you can see here, there's a 100-gram ball of clay and it's thrown. When it hits the block, it's at a speed of v. We'll just for to make things easier, we'll assume that this direction is the positive direction. The spring is attached to a wall, and thus, since this collision will lead to an offset, in terms of it would lead the spring to compress. The spring will naturally want to reinforce stability by trying to get back to the equilibrium position, and thus begins oscillation. So like kind of like that. The spring will kind of like move like this way. If you guys can think about it, if you guys kind of like want a picture, and it will do so since this thing is since this setting is ideal and we're neglecting things like air resistance and friction, this will probably go on forever. This spring will compress a maximum distance of 4 meters. 0.4 meters, not 4 meters. Okay. Oh, that was a horribly drawn M. That's a horribly drawn M. This will be well, you guys probably already know, so I'm not gonna really waste my time drawing too much of this. Let's get into the questions. So here you have A, which is to calculate the energy stored in the spring at maximum compression. B, which is to calculate the speed immediately after the clay sticks to the block, but before the spring starts really compressing. And then C is to calculate the initial speed of the clay. So basically, what is V? So what's being focused here, you can probably tell since this is a collision, is that this is a momentum problem, and this is, since the clay sticks to the block, this is an inelastic collision. It's a perfectly inelastic collision. So to find the energy that the spring contains is to just apply the formula directly, which is basically what is elastic potential energy, and then elastic potential energy here is always defined as 1/2 kx squared, where x is the distance you compress the spring, and K is your spring constant. So we know both of these. Maximum compression is 0.4 meters, K is 200. So you get 16 joules as your answer for part A. Now, although kinetic energy is not conserved in the collision, energy itself is generally conserved because there's no friction. So before the collision, all the energy in the system was the kinetic energy that basically was held by the ball of clay moving. And then at the end, which by the end we defined that the spring has compressed by its maximum amount, all of that energy would have turned into elastic potential energy. So so the kinetic energy before would be 1/2 of, well, ignore this, it shouldn't be, MB shouldn't be in there because it's not, well, so we would just use 1/2 of total mass, which is MA plus MB times V squared, is equal to the elastic potential energy. And we already calculated what that was. It's 16, so just substitute in all the values. So MA of the clay is 0.1, MB is 2, and so you would get V equals 3.9 meters per second by solving for V in this kind of equation. Now, like we have said before, this is a perfectly inelastic collision, and it's also, and momentum is also conserved. So P initial is P final. So I'm going to separate that. MA times VA is equal to MA plus MV, which is the total mass after the collision, times VF. So you could just solve, and you get VAI. VA initial is 81.9 meters per second. Question 10 is a very rare kind of question. Most questions AP Physics don't really talk about waves. It's more often like an extended topic that sometimes might be covered in class. So, yeah. So in this problem, someone is attempting to create a wave by suspending a string, like a very tight string, with a fork prong here, with frequency 120 hertz, and the other end of the string is passed over a pulley and is connected to a suspended mass. So basically, you can think about that if this system is agitated in any way. Sorry, I have to charge my computer. The battery's really low. So you can think about this is that if imagine this is like actually a constant, like just a solid object, and you just offset this mass by a little bit, this would create like a resonating wave, like a ripple kind of thing you can imagine in the rope itself. So imagine this is done, and the wave pattern has 4 loops, as you can see in the pattern. This does not mean 4 cycles though. A cycle is actually 2 loops. That what's shown in blue is 1 cycle. So this is actually only 2 cycles. Now, the length of the string from the tuning fork to the point where the spring touches the top is 1.20 meters, and the linear density of the spring is 1.0 times 10 to the power of -4 kilograms per meter, and this remains constant throughout the experiment. So what is the wavelength? What is the speed of the waves? And if there's a point on the spring that moves a total vertical distance of 4 centimeters, which means that, and then what is the amplitude of the the standing wave. So if this like amplitude here is 4 cent, if this like distance covered in total is 4 centimeters, by like this distance covered in one cycle is 4 centimeters. Sorry. What is the amplitude of the standing wave? So basically, what's the most important is in this is not how the thing is set up. It's not the configuration. It's that you know that this wave has 4 cycles. So the distance over the number of cycles is the wavelength. So basically, this is the formula D equals lambda F. B equals lambda. So you could just substitute it in. That's 1.2 meters over 4. That's 0.6. Sorry, not 0.6. 0.3. 0.3 meters. Okay. So V is F lambda. So this becomes 120 because that was the hertz. Hertz is just the SI unit for frequency. And you've probably heard this in music where, yes, when you're tuning to see that hertz is how many cycles, or how many cycles the sound wave completes in a second. So V is F lambda, and then you just substitute this in, and you'll get, it shouldn't be 0.72 but 0.36, but you'll get 120 times 0.3. That's 36 meters per second. Now, in one full cycle, you can imagine a particle traveling up, reaching this antinode, or like local maximum, I guess, and then moving down, hitting the bottom, the minimum of the cycle, and then moving back up again. So it moves up one amplitude, moves down one amplitude, moves down another amplitude, and moves up one amplitude. So in total, the distance traveled vertically is 4 amplitudes. So the amplitude is 4 over 4, which is 1 centimeter. This was because it was kind of like given in the part that this total distance was 4 centimeters. So that's everything. So if you guys have any questions regarding this, you're free to stay behind and ask them. Please unmute your mic when asking. If not, I guess I'll see you. I'll see you later, I guess. I'll not be in next week for the physics club meet, but I'll be in for one of the following weeks for another physics lecture. So I'll see you guys later then if there are no questions.